and take a screenshot.
It's like when you're solving for B. I mean, I've done it right.
Okay, so let's do a setup on this. All right, altitude of a triangle is increasing at a rate of 2 centimeters per minute, while the area of the triangle is increasing at a rate of 2.5 square centimeters per minute. At what rate is the base of the triangle changing when the altitude is this and the area is that? All right, so we've got some triangle. And there is an altitude. Come on. Not tracking right for some reason. Altitude. We'll call that H for altitude. And we have area. So area of a triangle is 1/2 base times height. And we don't really have enough information to get rid of a variable, so we're stuck with 3 variables. So, but we have enough other information so that when we plug in, we'll be okay. So next we'll differentiate with respect to time. So d dt of A versus d dt of 1/2 BH. And oh, I forgot to post this online in case somebody wanted to join us. Sorry. Can I still do that? Brief pause. You guys think about that. Take that second derivative. You got to use the product rule. Messed that up, didn't I? All right, back to work here. So the 1/2 is just a constant, so it's just going to hang around. So the derivative of b with respect to time is just db dt. So I get 1/2 db dt h that hangs around plus 1/2 db dh dt.
And then d
dt on the other side. And then it's just a matter of plugging in all the known information. So we know the altitude, dH dt, is changing at 2 centimeters per minute. We know the area is changing at 2.5 square centimeters per minute. So circling known stuff, that's known, that's known. B and H are given. Now let's see.
Yeah, we don't know.
H and A.
H and A are given. We don't need A, but we can use A and H to find B right here.
But can you that's the part where you're like, do you have to multiply the 1/2 to the height, or can you divide by the height? Because depending which way you do it, it marks you wrong.
No, it shouldn't. So here, to find the corresponding base, we would just plug in 90 for the area is 1/2 the base times 10.5 and solve for the base, right? And that gives you this number right here. And so then you can solve for dBdt. Okay, so you just got to be careful with your arithmetic there. All right, so I'm going to move on. Next is 8. What do we got? Page number 8. Heat gain, pressure change. All right, so is there a specific question about this one? What to do with it? Who asked this one?
I just tried it a couple times.
It wasn't working out. Okay, let's get it set up then. Clip. All right, so air expands adiabatically, that is without gaining or losing heat. Its pressure and volume are related by the following equation. P times V to the power 1.4 equals C. So that's relationship between pressure and volume. We get that constant on the other side. Suppose at a certain volume and pressure, we have a decrease in pressure of 15 kilopascals per minute. At what rate is the volume increasing at this instant? So there's a couple of ways we can approach this. I guess we could find that constant first. Otherwise, we have a C hanging around as a constant. And they give us enough information to find that because they tell us that when the pressure is 81 kilopascals, the volume is 470. So I've raised that to the 1.4. So that's going to be my constant. That's whatever that is, that's the constant C that we're talking about. Yeah.
The volume is in cubic centimeters, and kilopascals are in meters squared.
Oh,
Are we gonna have to do a
That's-
change there?
that's an issue, isn't it? So,
I don't run into any issues with that.
so what's the definition of a kilopascal?
1 Newton per meter squared.
Is 1 Newton per meter squared. And yeah, that's a problem because then we have cubic centimeters. So we do have to resolve those units. That could be the problem you would have been having. Question?
It worked out. I didn't have to do any sort of
You
conversion.
didn't have to do any kind of conversion. It just lets you run it without converting. You too?
Yeah, no,
Oh.
I.
Okay, well, let's ignore conversion for a minute and just see what happens. So that's my constant. So then the equation I'm interested in, come on, there we go, would be P times V to the power 1.4 equals that number, 81 times 470 to the 1.4. You could either choose to use the product rule on the left or bring the V or the P over to the other side and use the quotient rule or the, oh no, I guess that would work better, right? Yeah, if I can avoid the product rule, the quotient rule, something like that, I like to. So what I could do is divide the P to the other side. Then I'll get P to the -1. Does that make this any easier? No, that doesn't make this any easier. We're just going to take it as it is. So differentiating both sides with respect to time. I'm going to get a 0 on the right side. On the left side, I have to use the product rule. So derivative of P is just dP dt. And then times V to the 1.4 plus, this time P stays constant. We have to take the derivative of V to the 1.4, which is going to be 1.4 times V to the 0.4, because we've dropped the power by 1, times dV dt.
Oh, jeez.
So then, let's see, what do we know here? We know B, that's the 470. We know P, that's 81. We know dP dt, that's the 15. We know that V there, so the only thing missing is dV dt, which is what I'm trying to find. So hopefully we don't need to mess with any units. And we just plug those numbers in and solve for dV dt. All right, so I'm going to leave that one there. If there's still a problem, then we can talk later. Moving on. And again, I will post these notes if you didn't quite get all that. Look back at it. Number 9, is that what was next? The grain one, or gravel in this case. All right, screenshot. All right, so gravel is being dumped from a conveyor belt at a rate of 50 cubic feet per minute. So that's a change in volume. I'm just going to make a note of that. dV dt is equal to 50. And it forms a pile in the shape of a cone. So there's my gravel pile right there. Volume, hopefully you're getting used to the volume of a cone, is 1/3 pi r squared h. And the diameter and the height are always equal, okay? So diameter is equal to twice the radius. So I also know that twice the radius is equal to the height. So I want to get rid of the radius because the final question is how fast is the change in, is the height changing? So I don't really care about the radius here. So radius, according to that, is equal to the height over 2. So I'll substitute that in. I'm going to write that up here above. Come on, there you go. So now I have V equals 1/3 pi times h over 2 squared times h. So I have a 2 in the bottom squared, that's going to give me a 4. Combine that with the 3 in the bottom, I'm going to get a 12th. So I have pi 12ths times h cubed. Does that seem reasonable? Simplification there. All right, so I think I'm ready to do my implicit differentiation. So derivative with respect to time of this side and that side gives me dV dt equals the pi over 12 just getting carried along because it's a multiple. 3 comes down. Now I have h squared, and then chain rule says don't forget your dH dt. And then the given information here, I was given dV dt as 50. I'm asked to look at this when the height is 17, and now I can solve for dH dt. So just plug in those numbers, do a division, and we get an answer.
Better get that 2 times radius is height.
So we were given that the diameter and the height are always equal, and diameter is twice the radius. So that translated as this statement up there. If they didn't give me that, then I would also, like if they didn't say there was a relationship between the height and the radius, I would have to use the product rule on that, and I would have to know the radius at a certain time, and I would have to know how the radius is changing at a certain time. Yeah, so because they say the cone always has that shape, that makes it a little easier. All right, so hardest part on these is the setup. Hopefully your arithmetic following that is okay. Another question, new page, was number 11, is that correct?
Yeah.
All right, spherical snowball, melting. Let's grab that. Oh, we're gonna do another ball problem too today, cool. All right, so a spherical snowball is melting in such a way that its radius is decreasing at a rate of 1/10 of a centimeter per minute. At what rate is the volume of the snowball decreasing when the radius is 17? Note the answer is a positive number. Interesting, that's a bizarre note. Go with it. All right, so appendix, not happy about this corner of the board. So first thing we need to know is the volume of a sphere. That is 4/3 pi r cubed.
We're gonna have to memorize these for the test.
No, you don't need to memorize geometric formulas for the test. If you need them, I'll give them to you. The calculus formulas you need to know, and so we'll get a list of those as we move along. So let's see, we're given the rate of change of the radius, so dr dt is 0.1.
Isn't it negative? Decreasing?
Is decreasing at a rate, yeah. What rate is the volume? Why did they say node? And, oh, so they just want to say what's the decreasing amount. Yeah, so let's make that a negative. So we'll just ditch the negative when we go to state the answer. I guess is what they're saying there. Really not much else to do with this except take the derivative implicitly. So derivative with respect to time of each side is going to give me dv dt on one side. On the other side, the 4/3 pi are just hanging out. Derivative of r cubed is 3r squared dr dt.
And it gives you the radius of 17 meters.
Yeah,
Or
17 centimeters. So the units are matching here, which is good. So then we just plug in the given information, 4/3, the 3's divide out. Let's get rid of that now. 4 pi times 17 squared times negative 0.1. And that's that. Type that in, state the answer without the negative attached to it, because they want to know what the decreasing rate is. Decreasing means the negative. All right. So, next topic. Oops. Where's new page? We are moving on to section 2, linear approximations with differentials. We have a wonderful textbook you should take the time to open up once in a while. I have a print copy here if anybody ever wants to borrow it and take it home for some nice light weekend reading. It's a great book, it's not too heavy. So linear approximation of a function at a point, aka tangent line. We've done tangent lines. We know a lot about them. We're just going to take that process just a little bit farther and throw in a couple of other related ideas. So just a reminder about some notation. Yeah. So we're looking at differentials of the big idea. And we have, say, some y equals some function of x. We take the derivative, dy dx. We also call that f prime of x, right? And a while ago, we looked at the idea of separating the dy from the dx instead of looking at that as just this process we do, that they can be considered actual quantities. So dy is a quantity, and so is dx. So they're both measurable quantities is the way we're going to think about them here. So then we have what's called the differential form of the derivative. dy equals f prime of x times dx. So that can be sometimes a helpful way of looking at derivatives. It helped us in using the chain, figuring out the chain rule. It made that way easier to look at. Now, we also know, I had problems with my pen, here we go, that dy dx is also defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. If we make the assumption that h is a very small number, then we can say that dy dx is approximately equal to f of x plus h minus f of x all over h. And if it's small enough, then dx and h are essentially the same number. They're just little tiny quantities. So dy is approximately equal to f of x plus h minus f of x, if h is small enough. Otherwise, it's not close enough to approximate. What does that look like in a picture? Suppose that's f of x right there. And we're zoomed in. There's x. Over here would be x plus h. This distance in between there, that's our h, right? Change in x. Sometimes that's also called delta x. Now, we can calculate f prime of x, and what that's going to give us is the slope of that tangent line there. So m, the slope for that, is f prime at whatever x value we're at.
So it's dx approximately at h.
Dx and h, so dx is approximately h, is what I'm saying. So if h is small enough h, and h is approximately equal to dx. And so that means delta x and dx are about the same thing. So just keep in mind, when we find the slope of a line, we call that change in y over change in x. And we can do that for 2 points here. So for example, if I trace this up here, I'm going to get some other y value. F of x plus h is that other y value. Down here, I have the first y value. That's just f of x. And the distance between these two y values, that is delta y. The actual change in the y values. So I'm going to make a triangle here. So I've got a couple of different triangles here. I have this one sitting down below there. And then off the tangent line, I'm going to get a slightly different one. Let's see. There's a highlighter for that. No. So I get a slightly bigger triangle off the tangent line. So what are these quantities here? So off of this smaller red triangle, this is what I'm calling delta x, and this red segment is what I'm calling delta y. Off the tangent line, I get this slightly different y value up there. What the heck is that y value? That y value is the slope, f prime of x, times dx. Move that over a little bit. And in this case, dx and delta x are about the same value. So that right there is related to that differential formula. Okay. And we took a look at this a while ago. Remember we talked about marginal revenue and marginal cost? I used a similar idea when we were talking about that. So what we get from putting all of this together, so this idea here put together with this idea right there, is we get that the actual change in y, delta y, which is f of x plus h minus f of x, is always going to be pretty close when you zoom in to f prime of x dx. And so I'll talk about why we would want to look at it one way versus the other. We have two different ways of looking at it. We have actual change in y, and then over here we have an approximate change in y based on the tangent line. All right, so right now we're going to go into the manufacturing business. And we are going to manufacture ball bearings. So a ball bearing is a little sphere. Distinguishing characteristics of that sphere, well, to figure out the size of it, we need a radius. We need a certain amount of metal to make the ball bearing, so we need a volume. Volume is 4/3 pi r cubed. So let's suppose we're making large ball bearings, relatively large ball bearings, and let's say that the diameter is equal to 1 centimeter from our manufacturing equipment. Now, bottom line is when you make multiple things, they're as hard as you try to make them all identical, they're never going to be identical. There's always going to be a little bit of variation going on due to machinery, due to human work. So there's going to be a margin of error here. So let's just say that the margin of error on the radius is 1/10 of a millimeter. So that means, although most of the ball bearings are about 1 centimeter, they could be 1/10 of a millimeter too big or 1/10 of a millimeter too small in terms of the radius, right? So that could be up to 2/10 of a millimeter on the diameter. Okay. So if the diameter is 1 centimeter, what's the radius here? 5 centimeters.
5 millimeters.
Oh, sorry, 0.5. Yeah, I was getting millimeters next. It should be 5 millimeters. So what I want to figure out is if there's a range of possible errors, right? It could be anywhere from negative 0.01 up to positive 0.01. What's the possible change in volume here? That's the question. What is the possible error in volume? Okay. In other words, I'm looking for the rate of change of volume with respect to the radius here.
Oh, you sent me some weirdo. What's up, Nick?
And mostly what I care about is the dV part, change in volume. So a couple different ways to look at it. First, I know that volume is a function of R, so the actual change in volume is going to be the volume at my error, so R plus H, minus the volume at the actual radius. So for this particular one, that would be the volume at 5.1 centimeters versus the volume at, minus 5 centimeters. We'll make that calculation a little later. The other one is calculating the differential for the volume. So to get the differential, I need to take the derivative of volume with respect to R. So that's derivative with respect to R of that 4/3 pi r cubed. Now notice the variable I'm taking the derivative with respect to is the same variable I have, so there's no chain rule here, right? Unlike the last section. So this is just going to be 4/3 times pi times 3 times r squared. If I put this in differential form, I just throw the dr to the other side. So dv equals, and let's clean this up a little bit, 4 pi r squared dr. Does anybody recognize the formula 4 pi r squared? From geometry class, way back. That turns out to be the surface area of a sphere.
Oh, that's horrible.
The derivative of the volume of the sphere is the surface area. The rate of change in volume.
Is that for all shapes or just here?
I think it's for all shapes, because the way to think about it is the surface area, imagine that as a layer of paint, right? So if you imagine the snowball melting, that outer layer is like stripping off a layer of paint. You just took off a small chunk of surface area. So the rate of change of volume should be, does that make sense now?
Yeah.
Thinking about the snowball melting kind of thing, and like a layer of paint, yeah, should be the surface area. It's kind of cool. All right, so now we just take the information we have and chug it in here. We have known information that we're concerned about a radius of 5 millimeters and a margin of error of 0.1 millimeters. And so plugging those in is going to give us the change in volume. So let's try it. 4 pi times 5. And I'm not going to worry about the units at this point. Can you see they're going to work out?
Mhm.
We're going to have millimeters squared times millimeters, which is millimeters cubed, which is a change in volume. Forgot the square. Yeah. So whipping out your calculators, what does this come out to? .1415. It comes out to pi exactly here because 4 times 25 is 100, and this is, oops,
10 pi.
10 pi.
That's 30.
Oh, I wanted that to be 100th of a millimeter. Oh, wait, we'll leave it as a 10th of a millimeter.
Yeah.
So it's 10 pi, so it's, yeah, so this should come out to 31.4159. I forget the rest of the digits. Something like that.
15926535897.
So what is this right here? This is the maximum error that we're going to see in the volume. Okay. So it's possible if a ball bearing will come out a little bit too big because the radius was a little too big. So that means it'll use a little over 31 cubic millimeters of metal more than it should. Now it could also go the other way. We could end up using that much less metal than we should. Okay. So that's the amount of error. Is that a big error in the size of the ball bearing or a small error in the size of the ball bearing? To judge that, we have to look at what is the actual volume. Okay. So then we have to find percent error. So this is the actual error. We're going to find the percent error next. The percent error would be the change in volume divided by the actual volume rated as a percentage. So for us, we've got our 10 pi was our differential change in volume. The actual volume will be 4/3 pi times 5 cubed. And so what does that come out to be? Oops, there's Desmos. So I have my 10 pi divided by my 4/3 pi times 125. So I get 0.06 would be 6%. When we change that to a percentage. And this is what's called relative error or percent error. The actual error was about 31 cubic millimeters, right? The relative error means relative to the size of the object was 6%. If this was a bigger ball bearing and we were off by 31 cubic millimeters, then the percent error would be smaller, okay? So those are some of the things we can take a look at. So somebody might say, whoever's running the production line here, 6% error per ball bearing max is just too big. We got to get the machines to get that radius closer. So those are some of the things this kind of calculus stuff can be used for. What's that? You think it's interesting? Yeah. And other things that we look at is, so I'm using calculus to estimate the error. This right here is the actual error. Why would we use the differential error as opposed to the actual error? Well, the reason is often the curve or function that you're working with is complicated and hard to work with. Cubes aren't that bad. Sine and cosine, they're a bit of trouble, and other functions can be more trouble. The thing is, it's way easier to calculate on a line than it is to calculate on a curve. So that's why differential approximations are used in reality often. Okay. So I'll show you another place we can use this. And then we'll grab a homework problem. I think we have time for both. So anytime you have to do an approximation, often the differential approximation can help you do that. So what we're going to do is look at approximations for a square root. How do you take a square root? Anybody know? You push the button on your calculator, right? Okay. How the hell does the calculator do it, though?
It
picks a number at some point between the original number and its square of the number until it gets close.
That's one technique, and we'll look at that technique later. It turns out there's a bunch of techniques for calculating square roots. So I was at the age when calculators were just starting to come into like elementary school, middle school. And so they were stopping to teach how to do square roots by hand, because you used to have to do it by hand or on a slide rule before you had a calculator you could push a button on. Or you looked it up in a big book. Right? Those were the ways to do it before.
So you take the closest square, and then between those two numbers, you just guess until you cancel it.
Sort of, yeah. We'll look at a way of using a tangent line to make that idea a little more efficient at the end of this chapter. For now, we're just going to use a straight differential to pull it off. So this is warming up to that idea. So let's say we got the function f of x equals the square root of x. Okay. What's f prime?
1/2 x. 1/2 x to the negative.
2,
Or negative. Yeah.
1 over 2 square root.
Yeah, so we have those two versions of it. I'm going to go with the second one. Okay. So here, change in y is equal to f prime of x times the change in x. Okay. And here I'm kind of interchanging dx and delta x. That's kind of almost legal if they're small enough. So I should say approximately there, because I didn't use the dx. Other thing to think about is the actual change in y. That is f of x plus h minus f of x. Playing with this a little bit, I get f of x plus h is equal to f of x, the original function value, plus whatever the change in y is. Right? And if delta x is small enough, then dy and delta y are the same thing, close, almost the same thing. So then what I get is that delta y there can be replaced with this up here, f prime of x times delta x.
And what do you mean by small enough?
Less than 6% error.
How do we determine that?
Small enough is you're right, it's a very vague term, and it just has to be small enough.
Okay, I'll take your word for it, Gary.
Yeah, so if we're working with numbers like the size of 1, I would want h to be, and again, it depends on the function too, like the curvature of the function. Because going back to this picture, oops, here, depending on the curvature of the function, this distance up here is what is the difference I'm missing out on, right?
Okay.
So if the function is wicked curved, and I'm not close enough with x, then that means this distance is going to be bigger. That error, that change in between delta x and dx is going to be bigger than I want it to. So there is no way I can give a definite answer on what is small enough. It depends on the problem.
Okay.
That's one reason we look at, say, percent error after. Okay. So the question with the ball bearing is this small enough? And if we make millions of these and we're always with around 6% off, that's going to add up to a lot of lost metal in the end, and lost profits and stuff like that. So here we could say, hey, this relative error is too big because of the financial constraints. We've got to get these machines to work better.
Or you gain metal.
Or yeah, it could be we're off in the other direction, right? Yeah, because this is a plus or a minus. So that means more work needs to be done to see which way we're off more by. If it's balancing out, so what? We're good. Okay. Yeah. So that's only part of the story, right? Yeah. So what's small enough? It varies from problem to problem. That's why we look at the actual error and the percent error, and then a judgment can be made by there. But it is a judgment call. Somebody has to go in and say, I think this is not good because it's not close enough because. But this formula right here is what I was getting at. This is the idea of using a tangent line to approximate what the function's doing, is what we're doing there. Okay? Because lines are easier to work with. So here's the problem we're going to apply this idea to. We're going to consider damn it. There we go. We're going to consider finding the square root of 16.5 without a calculator. To do that, we're going to let x equal 16, and we're going to let delta x equal 0.5. Okay. So that right there is my f of x plus h, but I'm calling h delta x instead. So I'm trying to calculate what is f of 16.5. And our differential formula says, oh, to do that, get f of x. Well, here, f of x is pretty easy to do, right? That's just the square root of 16, which is 4. We can handle that one. And then it says to add on f prime of x times delta x. So for us, f prime evaluated at our x value is going to be, let's see, 1 over twice the square root of 16. Oops, that's supposed to be a plus, sorry. Times my delta x. So here's a question. Is 0.5 small enough here? We'll find out in a second. So we can compute this pretty much easily by hand. That's going to give me 4 plus 1 over 2 times 4. And 0.5, I'm going to write that as a half. 2 times 4 is 8, times 2 is 16. So this gives me 4 and 1/16 as the approximation of the square root of 4 1/2. So let's see how we did. 4 and 1/16 is 4.0625 versus the square root of 16.5, 4.0620. So I'm accurate to almost 3 decimal places here.
That's pretty good.
Okay, that's not bad, right? And I could do this, now I have to do calculus instead of using a calculator. But then we got to say, somebody had to program the calculator to find a square root to a certain amount of accuracy. How do they do that? This is one step toward making that happen. So we're going to learn a routine based on this idea by taking it a few steps faster. And so there's a way to repeat this process and narrow down the answer like that. All right, let's see what's in store for you on the homework. We're almost out of time. In 2 minutes, can I set up a problem?
1 minute.
1 minute. Let's try number 7. Number 7 seems to be interesting. Oh, that's just like what we did. Okay. Number 5, maybe. A circumference of a sphere was measured to be 77 centimeters with a possible error in 0.5. Use linear approximation to estimate the maximum error in the surface area.
We can keep it at centimeters, right? Like we don't have to always do millimeters.
Yeah, so can I set this up in 30 seconds? Probably not now. Just lost 5 of them. All right. So sphere, draw a picture. I was just given the circumference. C equals 77. And I was just given a change in C of 0.5. And I want to relate that to the surface area. So the surface area of a sphere is 4 pi r squared, which I mentioned earlier. Circumference, anybody remember how to calculate circumference?
2 pi r.
2 pi r. So that 77 is 2 pi r. So we have to link those together because what we want to find is d of the surface area. Which means I need to find the derivative of that. And then multiply by delta r. Ooh, how am I going to find delta r? Of that. All right, I'll let you guys focus on that tonight. We'll go over that tomorrow if you get stuck on it, and any other differential problems you get stuck on. Good luck. Have a great fall day.